Welcome to Lecture 6. I want to recap some of the things that we discussed in Lecture 5 about Newton's laws. So just to reiterate, Newton's first law, we discussed about having the situation where you could either have constant velocity equal to zero or constant non-zero velocity. Either way, that's covered by Newton's first law, which basically tells us that whenever you have no net forces on an object, you will have some sort of constant velocity. On the other hand, if you do have a net force acting on an object, then Newton's second law tells us how that object's velocity will change in response. The net force is going to be proportional to the acceleration, pointing in the same direction as it is a vector quantity as the acceleration, and also proportional to the mass. And Newton's third law we discussed basically tells us that forces come in pairs, often referred to as third law pairs, force pairs, and it basically says that if object A is exerting a force on B, then you're going to have an opposite force exerted by B onto A. And then we discussed the kinds of forces that you're likely to encounter in our problems that we have to solve. We talked about tension, friction, and the normal force, and also the weight force. And then we discussed an important tool that you should use whenever you're starting your problem solving process, and that is to start by drawing a free body diagram. On the free body diagram, you will represent the object as simply a dot, and then you will indicate the magnitudes and directions of all of the forces as individual vectors emanating from that dot. You don't want to include any forces that the object itself exerts. These are only forces that are exerted on the object you're trying to analyze. So I know last time I said we were going to do some problem solving examples after we've drawn a free body diagram, but I wanted to take one more opportunity to go over an example in depth with you on free body diagram drawing, and the reason for that being that drawing these free body diagrams accurately is really a crucial step in understanding how to successfully apply Newton's second laws, because you need to know how the forces interact with each other and which forces might be equal to one another and so on. So let's take an example that is a little bit different from the one that we discussed last time. You still have one object on top of another object. This time they are crates inside of an elevator. The elevator is moving upward at a constant speed, and we know that crate A has a greater mass than crate B. And so we want to draw a free body diagram for each of these crates. And so we want to know, first of all, in what direction the net force on crate A points. So you can pause the video if you want to figure out what this is, and then when you come back, hopefully you were able to deduce the correct answer is C. If you weren't able to deduce that, I would encourage you to go back to the problem statement and read the words constant speed. Sometimes we have buzzwords like this. We talked about, for example, at rest, meaning velocity equal to zero. Constant speed tells us that right away that there is no acceleration. Well, I guess it doesn't right away necessarily tell you that if something is moving in a circle, but this elevator can only move up and down, and if it's doing so at a constant speed, that means there's no acceleration. And if there's no acceleration, then Newton's second law is going to tell us that then there's no net force. Okay, so the next question in getting set up to draw these free body diagrams, we want to make sure that we're indicating the magnitudes of these force vectors accurately. And so the next question asks us to consider which of the following forces will be the smallest in magnitude. Okay, for this one you need to be very careful. Go ahead and pause the video if you would like. When you come back, let's see what we can figure out here. So because this elevator is moving at a constant speed and there's no net force involved, as we deduced in the previous slide, then really this situation is basically identical to when we had one book on top of another book. And if you remember, when we drew those free body diagrams for the two books, we had that the top book had two forces on it, the normal force of the bottom book on the top book, or in this case the bottom crate on the top crate, and the weight force. And then the bottom book, or in this case the bottom crate, so this is A and this is B, crate B is going to have its weight on it as well, and it's going to have a normal force on it as well. We'll call this of the elevator on the crate B, and then it will also have the normal force of the top crate. Sorry, this is getting a little cluttered here. Let's see if I can make it a little clearer for you. Okay. Last time when we were talking about the books, we decided that by Newton's third law, we could assume that this normal force and this normal force were equal to one another. They are third law pairs. So this force equals this force. And then we said that by Newton's second law, because this is not accelerating, then we've got a situation where this normal force must be balanced with this weight force, otherwise it would be accelerating. So these two are equal to one another. Okay, so if we're looking for the smallest magnitude vector, I've actually drawn it accurately here, but the question is why? Okay, why should this one be the smallest? How can I know that that's true? Well, I know that crate A has a greater mass. If it has a greater mass, then it's got to have a greater weight because weight is equal to mg. So this weight is going to be greater than this weight, okay? And I know that this weight is also equal to this, so this must be less than this. How do I know that it's not this one that's the smallest? Well, remember when we were talking about the books that these things have to balance. So what's pointing up has to equal the sum of what's pointing down. So by this equation here, I can see that this top one actually needs to be a little bit longer probably to reflect the fact that it is the sum of these two bottom ones, meaning that this weight force must be the smallest. Now don't get confused and think that this weight force has somehow changed by the fact that box A is on top of it. The weight of the Earth acting on box B is going to be the same no matter what. It's defined to be m times little g. And just because I set this other box on here doesn't mean the weight of box B has changed. It's just got this additional downward force from the normal force acting on it. Okay, so if that was a little misleading in the last lecture, I apologize. When I was redrawing the vectors, I merely meant to say that, okay, in actuality, this should be smaller. And that's the same thing that we have here. Okay, so another question. When we were doing this analysis, we were able to conclude that the weight of the Earth and the weight of the normal force were the same, right? So they had the same magnitude. How did I know that they had the same magnitude? Which of Newton's laws did I have to use? Well, it was not Newton's third law, right? Because the normal force, we decided it comes in pairs of A on B and B on A, so that has nothing to do with the Earth acting on A. So this came by way of Newton's second law, as we were discussing on the previous slide. So a slightly better version of the final free body diagrams can be seen here. And you see that the weight of the bottom box is the smallest of the vectors portrayed here. Meanwhile, this vector, and this vector are all equal to one another, and this one is the greatest. Okay, so we're going to change the situation a little bit. Let's say that instead of the elevator moving at a constant speed, it's moving up. However, its speed is slowing down as time goes on. Crate A is still more massive than Crate B, but now we want to make a free body diagram of this alternate situation in which the elevator is actually slowing down. So we want to know in what direction the net force is going to point in this case. If you've paused the video and you've come back, hopefully you've been able to deduce that the net force is going to point in this direction. How do I know that? Well, let's think about it. The elevator is moving up. This is the velocity vector. If it's slowing down, in order to shrink that velocity vector, my acceleration vector must be pointing in this direction. And since force, the net force, is proportional to the acceleration and pointing in the same direction as the acceleration, then that also has to be the direction that the force vector points in. Okay, so the next question about this new situation is very similar to the previous situation that we were looking at, except again now things are slowing down, but we want to know which of the following forces is going to be the same in magnitude even though it's no longer going at a constant speed. Okay, so the answer to that is your weight force, right? Normal forces can change, but your weight force is defined to be mg. Okay, so these normal forces, these vectors are going to be different than they were before when we draw our free body diagram, but the weight force will be the same. And I should say that goes for box A as well. All right, so what about the normal force of A on B compared to the normal force of B on A? Well, Newton's third law still applies, so these are still going to have the same magnitude, even in this new situation. So what you see then as a result are the following two free body diagrams, where you still have the weight force of B being smaller, okay, but now this normal force has shrunk too, and these have as well, even though they are still equal to one another. Okay, and to finally recap Newton's laws before we, in the next lecture, start applying them to problem-solving situations, I would encourage you to look at this video where there's a great summary of each of the laws and what they really mean conceptually. All right, we will go over some examples next time.